So I'll be talking about dense triangle-free binary matroids, and this is based on my master's research under Jim Whelan and Peter Hansen. So first of all, since I'm talking about binary matroids, triangle-free binary matroids, I sort of need to mention Bose-Birken again, since Peter mentioned it. Namely, if M is a simple triangle-free rank R binary matroid, then M has density at most a half. Here, density is taken to be the size of M over 2 to the rank, as opposed to over 2 to the rank minus 1, which is the size of the projective geometry. And this is just because the structure is more related to the exponential nature. And again, quick proof. If you just take a point in M, consider all the lines going through this point. You can only have, since if you want it to be triangle-free, you can only have one point from each of these lines. So since it's 2 to the r minus 1 lines through your point, you can have a total of, at most, 2 to the r minus 1 points. And the bound is achievable by affine geometries, which are just projective geometry minus hyperplane. So the general question that I'm considering is what's the structure of triangle-free binary matroids with density strictly greater than a quarter? I'm going to be assuming for simplicity that all our matroids are simple, and it will often be useful to think of them as subsets of binary projective geometries. So we do have conjecture. I'll be getting into it later in the talk because it does involve some power. Although I'll now mention a few weaker conjectures that follow, just to give you some ideas of them. So first of all, we have that we conjecture that for any epsilon greater than 0, there's an integer k, so that in any rank, there are at most k triangle-free binary matroids that beat a quarter density by at least epsilon. So for example, if you take epsilon is equal to 1 over 16, it's been shown that we only have one maximal triangle-free binary matroid that beats density a quarter by at least 16. And namely, these are the affine geometries. And just this year, we've also have that if you take epsilon equal to 1 over 128, there are at most 8 maximal triangle-free binary matroids in any rank that beat that have density strictly greater than 3 over 128. So another conjecture that actually tells you a bit more about the structure is that if M is a triangle-free binary matroid with density strictly greater than a quarter, then it has critical number at most 2. Namely, M can be partitioned into affine binary matroids. And so far, we've proved this all the way down to 33 over 128. So why density a quarter? As Peter already mentioned in his talk, quarter is sort of a critical threshold for triangle-free. And in particular, less than a quarter density, we have a family of triangle-free binary matroids with arbitrarily large critical number. That is to say, below a quarter density, class of triangle-free binary matroids gets chaotic. So now I'm going to give a few constructions of how you can have triangle-free binary matroids with density strictly greater than a quarter. First of all, I'm going to give a way to lift constructions to higher rank matroids, namely by doubling. So if you have a triangle-free binary matroid, as as the name will suggest, you double all the points and then you lift the duplicates towards an ambient point in the projected geometry, although you will not include the point. This will remain triangle free because, first of all, you're not creating any triangles through the ambient point you're lifting towards. And if you take any hyperplane that does not pass through that point, the restriction to the hyperplane is going to be exactly your original triangle free binary matrix. So you can repeat this doubling if you have k times. It will generally look like having a rank k flat that you're lifting all the points in your original matrix. So an example is if you take a point and lift and double it k times, you just get the affine geometry of rank k as well. Homomorphism. There's sort of the inverse operation of your doubling. So if you have a binary Matroid in some ambient projected geometry, and you take some flat A that has zero intersection with your Matroid, we'll say that contracting out by this flat is a homomorphism. This is sort of analogous to graph theory homomorphisms, where you add an edge that's not originally in your graph and then contract it out. So if you have a flat of corank k and A is of rank k, if you look at the cosets with regards to A, anyone that is not empty will have a homomorphism to a point, and the cosets that are empty won't appear after the homomorphism. So because doubling did not create triangles, we have the lemma that if n is a simple triangle free binary matroid and m has a homomorphism to n, then n will also be triangle free. So another conjecture we have is that if M is a triangle free binary matroid of rank R that has density strictly greater than the quarter, plus 1, so it beats a quarter by more than just 1 point, then it will have a homomorphism to a smaller triangle free binary matroid. So this is a very strong conjecture because we're saying that the only ones that don't reduce to smaller examples are the ones that beat the quarter of density by exactly 1. So you can get more than a quarter plus 1 density, but the only way to do that is through the doubling operation. So for example, binary rank 5 spike, this has size 10, so it does beat a quarter density by 2 points, and it does indeed have homomorphism to C5, which is a small triangle free. So how can we construct triangle free binary matroids that have density just 1 over the quarter? One sort of easy example is affine plus a point matrix. If you take an affine geometry and then add a point in complementary hyperplane, you partition the points in the affine geometry by the lines through the new point. Since you want it to be triangle free, you can only take 1 point from each of these lines, and the resulting matroid will be triangle free. Note there's a whole bunch of possibilities for your matroid, because for each line you can choose one of the 2 points. So I think in rank 7 there's something like 40 of them. Yeah. So So far we've shown that if M is a triangle free binary matroid of rank R with density strictly greater than 33 over 128, then M will have a homomorphism to one of these affine plus point matroids. This does need to be strict inequality because it is not true if M has exactly 33 over 128. Namely, we do have two matroids on 33 elements that aren't affine plus point. They are triangle free and have a density. So I am going to describe how the structure of these and how to get them, but first I'm going to talk about exploding a triangle. So if you have a triangle, you pick 1 point from your triangle, and for the other 2 points you lift them and sort of double by some rank k flat. But then you can only, because you want it to be triangle free, you can only take for each line through your point, you can only take 1 from each of the cosets. So this is actually going to be affine plus point. So you're exploding a triangle into an affine plus point matrix. And I should like the name exploding a triangle because you do have a lot of options. So now going back to constructing our non-affine plus point matrix. If you take a 5 cycle, then you just add some point in the ambient projected geometry. You do create exactly 1 line. So for 1 triangle, so then for all the points not in the triangle, taking the rank 3 flat, in an ambient projected geometry rank 7, you double all the points not in a triangle, and then you explode the triangle. And then putting them together, you can show that this is a triangle free matrix, and this is 33 elements. You can also show that all the points that are not included in the coset that you sort of removed when for it to be triangle free, if you add them back in, you only create 1 triangle. So you can repeat this process of having a unique triangle and going back. In general, if we have a rank R matroid with only binary matroid with only 1 triangle, having a rank K flat, and if we repeatedly double K times all the non-triangle points and blow up our triangle, we create a triangle-free binary matrix. And note all of these beat a quarter by exactly 1 point. So our main theorem now is that our main conjecture, our big main conjecture at this point is that M is a triangle-free binary matrix with rank R that has strictly greater than a quarter density. Then M has a homomorphism to an exploded triangle matrix, a matrix that's constructed in this way. So partial results, what we have so far. Series of events. First of all, if M is a maximal triangle-free binary matrix of rank R, then we can show that one of the following must hold. M is either an affine geometry or M contains C5. If M is not an affine geometry, then it must contain an odd cycle. So taking a minimal length odd cycle, take 3 points from this odd cycle, consider the sum. The new point, the sum of the 3 can't be inner matroid because otherwise we'd create a smaller odd cycle with the remaining points. So why would this point not be inner matroid? Namely, in particular because adding it would create a triangle. So there must be 2 points that it would form a triangle with. But then taking these 5 points, we actually actually create a C file. Well, we'd have a cycle, an odd cycle, and we know it can't be a triangle because it's triangle free, so this would be C5. Then we have another lemma. If n is a triangle free binary matrix, rank R, that beats quarter density, it's either an affine geometry, an affine point, or contains the binaries 5 per rank 5, which were from our 233 element matrix. So to prove our conjecture, we're looking for a sequence of lemmas that sort of look like this. And after this, we'd want to have one with a longer list, and eventually we'd hopefully prove the conjecture. So instead of just triangle free binary matrix, if we think of projective geometry of some rank n, free binary matrix with possible structures coming out. One way to construct such a matroid is to take a flat of co-rank n-2. So then any rank n flat in a matroid would have to have non-empty intersection with it. And because the co-rank n-2 flat is triangle free, you won't be able to have that a full flat of rank. So we conjectured that if you have given high enough density, such constructions where the rest of the geometry is completely filled are the only such PG n-1, 2 free binary matrix. And that's the end of the talk.
Any questions?
So the conjectures that you've got, the one, I mean, you feel, well, the one that you had a specific is with the spikes and things. Do you really believe you've encountered everything there, or do you?
So we have it to rank 7. It looks plausible, but I mean, so far we've just had a sequence of conjectures that we found counterexamples.
Yeah.
but so far this is the one that seems the most yeah. Or we've looked at higher
Just
conjectures.
the one you have for example.
Yeah. Yes.
I've got a question. Are your exploded triangle matroids, do they bear any relation to the triangle-free graphs with density just above a third that Brand and Tomasi found?
So they were using generalized pentagons, right?
Mm-hmm.
That, I mean, you've seen some of what we were doing, but you know, where you double and add the gadget, right?
Mm-hmm.
That was more related to the generalized pentagon. The graph theory analog of this is a bit messier. It would probably be a bit more general than the generalized pentagon. But yeah, you need more prior conditions.
Any more questions? Thanks again, Marco.